Thank you, National Instruments, for hosting this and allowing me to come talk a little bit. I'm actually going to be talking about something a little different than everything else we've been seeing to date. I'm going to be focusing on streamlining MMIC design with a focus on high power and high frequency applications. So more as we're moving into the upper microwave and millimeter wave applications, what are the types of things that we need to consider as we're doing our designs? So what is it we're trying to do as a MMIC designer? Obviously, we're trying to optimize performance of our circuit. We want to make something that is producible. When you're doing a MMIC design, you don't have a lot of opportunity for tuning at the end of the process. Once you get a circuit out, it's more or less what it is. There's a lot of cost and a lot of time that goes into a MMIC fabrication, so you want to make sure you have something that can be reproduced. You want something that's robust and reliable, so that is very much process dependent, but it's also something that can be impacted greatly by the design. And obviously we're trying to reduce the cost and size so that we have a product that's going to be appealing to our customers. But at the end of the day, we want to design an amplifier that's working for our intended application. And what does your program manager want? He wants you to meet cost and schedule. He doesn't care about any of the other stuff, right? So with this in mind, as a MMIC designer, I'd like to take as much time as I could, put as much effort as I can into getting the design right because of the implications, particularly with the MMIC of getting it wrong. But we need to find ways to make that efficient and streamline it so that we can get things in a timely manner. So what are the various things that we have to consider? A lot of the things that we would with any other PA design, obviously, but there's a few things that go into it that we haven't had to look at for the lower frequency things. Generally, we want a very good device model. As we've been talking about behavioral models, compact models, essentially as an end user, you want something that's usable and works. We obviously provide compact models at Wolfspeed. The reason being we have a plethora of different users with different applications that need something that is scalable, can be used under different conditions, and in order to achieve something like that, we need a compact model that is scalable and can be used under those different applications without having to go through the various levels and intensity of measurements that would be required for other models. You have to understand the process limits, because on a MMIC you are much more restricted as to what you can handle as far as voltages on capacitors, currents through your transmission lines. You need a yield analysis. Obviously, thermal effects are very important in any PA design. With a MMIC design in particular, you actually have some control over things like the layout of your FETs, and that can have an impact on thermal. So being able to actually simulate that and know how that's going to affect under a drive condition, what's going to happen is very important. And then, of course, as you move into the higher frequencies, things like EM coupling, effective line lengths, distributed effects, for any amplifier, obviously stability. If you don't have an amplifier that's stable, you don't have anything. And then because of the amount of time and cost that goes into each of these runs, you want to do as much on the back end of the design to verify that you've actually got something that's going to be what you put into the design. So, number one, how can we actually accelerate the design process and keep this streamlined? Number one, use a robust PDK. So make sure that you have models that are scalable, that they are accurate, and that they are usable. Secondly, same thing for the robust passive components. You want components that are well represented in the PDK, but also account for the various intricacies of each fabrication and the rules of each individual foundry. You want something that's going to account for process requirements. So even if there's not a DRC, there may be other limitations on your design. As I mentioned, there may be limitations on the voltages you can apply to specific capacitors, the amount of current you can put through a transmission line. There may be areas, as I'm going to talk about later, where you have to actually round things in order to accommodate those types of voltage limitations. And you want something that is integrated. So you want a single package that's going to allow you to do your DRC, your connectivity, EM, and simplify the layout. Beyond that, some things that I've seen as both a designer someone who's managed a MMIC design group and also has to deal with external customers designing into a foundry, there are some very simple things when you're doing a MMIC design that will make your life easier and also easier on the foundry who's doing it for you. So use hierarchy. Take advantage of the symmetry that you're going to see for larger power PAs. It'll not only streamline your process, but it makes it easier when we are doing the verification and the checking. Use segmented networks in order to accommodate stability simulations. So there, for multi-stage devices, obviously places that you can break to do your stability. Use the hierarchy that I'll be showing here in order to put those into areas that simplify that particular analysis. And also use areas of hierarchy wherever EM is needed so that you can easily switch back and forth. EM is very nice for getting the accuracy, but as far as figuring out how it's going to actually fit into the limited footprint, there's some complications. You need to be able to optimize things, having a way to switch back and forth and understand how those changes in the layout are going to affect the network can be more easily addressed if you take proper use of hierarchy. And then, in general, just judicious use of your EM simulations, integrating thermal issues early, and design checking. So a quick word about the process design kit. So one of the main advantages, if not the main advantage, of using a PDK is for the array of uses that our MMIC Design Foundry is used for, is the usability of it. And by usability, you need to be able to scale the device, depending on your frequency and power levels, into a usable cell. If you're using a discrete, you have a known power density and a known periphery that you can use. Oftentimes, when you're doing a custom MMIC, you are very much windowed as far as what your dissipation can be, under what thermal conditions, and putting out more power, even if you have the efficiency, can still be an issue for thermal handling. So you're often in a very tight window. Having scalability is key. Also, configurability, being able to swap between a device that has internal slot vias for the ground and a device that maybe has floating sources for source to generation in a low noise amplifier, for instance. It needs to accommodate self-heating. So for instance, we have handles for both the thermal resistance and base temperature. You can do a simulation, you can understand within your particular package what is the actual, and given the actual layout of your circuit, of your FET, what is the actual thermal rise that you need to account for. Having access to the internal current source through the model itself so that we can take advantage of harmonic tuning and waveform analysis. And then having the associated artwork automatically included so that you don't have to worry about making DRC errors, and that is key. So just a quick demonstration, got some of the various FETs that you can, as far as layout configurability, down from a very small, high-frequency individual cells, on a, say, 100 micron by 4-fingered device, up to something that has 500, 600, 700 microns per gate, multiple fingers per cell for lower frequency, high power devices. Additionally, parts that have air-bridged vias so that you can actually use source to generation, or if you wanted to use this in a common gate versus a common source, it gives you that kind of flexibility. And similarly, we're implementing all of our matching actually on the circuit, so having various MIM capacitors. We offer 2 different types with various capacitive densities. Being able to implement inductors with our design rules. As you can see, having to lay this out yourself would be very time consuming, getting the stack up right, making sure you have the rounding correct, the air bridging. Being able to just define this as a schematic element and have it properly implemented saves quite a bit of time. And then also various resistors with the implemented models that include things like contact resistance, thermal dependencies, also make design much easier when you're talking about quick implementation. And then also, as I mentioned, our particular foundry, because of the high voltages that we run at and the high current densities that we often have to accommodate, requires certain things that you wouldn't see possibly in other MMIC processes. For instance, all the corners of our capacitors need to be rounded to avoid field issues. It's a reliability issue. This automatically accounts for it and accounts for the variation in the capacitance that you get from the change in that area. Similarly, as I mentioned, the stacked spiral inductors, having the rounding, being able to accommodate spacing rules for DRC in order to get the proper implementation in the fab, automatic air bridging of the underpass and the overpass, and then even more useful, all the bridge code for connecting each of these elements is automated within the PDK. So you don't have to worry about things like making transitions properly, how you're going to accommodate moving from, say, a stacked metal to a non-stacked metal, from a via to a capacitor. It's all automatically accounted for. Makes designing much quicker. And then obviously you want something that has all of the integrated configuration definitions for the design. So that includes things like EM stackups, substrate definitions, the actual layer mapping for when you're exporting this to us for fabrication. Additionally, the EM definitions, how each of these layers actually gets mapped into the integrated EM to properly get the configuration. This alone, can save you hours of setup time and uncertainty. This is probably one of being able to use this and set this up if they haven't actually implemented this before is one of the most numerous questions that we get as a foundry. And then obviously you want to be able to fully verify your MMIC at the end of the day before submitting it for tape out. So having full DRC, this is not the full stack, this is just a window, obviously. And then connectivity rules so that you can do connectivity and LVS checking. So as I said, hierarchy is one of the easiest ways to speed your design. This is a photo of a commercially available MMIC that we have at Wolfspeed. And you can see during the design process, there are a lot of places that you can accelerate the design process by taking advantage of the fact that you're breaking this into symmetric areas quite often. And this has two advantages. Each of these layouts, you only have to accommodate once. When you export this to us and we're doing our DRC checking, if we find an error and you haven't used if you haven't used symmetry, it may get fixed in one area and not in the other. So there's always the chance that you're going to have a leftover layout error in the design. And then also when it comes to simulating for stability, particularly odd mode stability, which in these higher frequency and higher power MMICs becomes a significant issue, taking advantage of the symmetric design and the hierarchy will make that a lot easier. So as I said, simply breaking up along the symmetric lines allows you not only to take advantage of simplifying the networks, but it also allows you to use scalability in the MMICs, multiplicity in each of these cells. That'll actually increase your simulation time, regardless of the complexity within there. So that can speed the design. It minimizes layout time because, as I said, you have to do each of these sections one time as opposed to laying it out 4 times. It actually helps with stability checking when you do this, because for simple linear stability checking, K-factor, we can do a break along the first and second stage line, and then for odd mode, similarly, we can do a break along each line of symmetry to do those verifications. So just very quickly, simple small signal stability. Very useful, obviously. K-factor and mu, or mu1 and mu2, or mu and mu prime as they're sometimes known. Very useful. K is nice in that when you're doing the full amplifier, you can actually get K above 1 and still have an unstable amplifier. When you're actually breaking it up, you can use superposition to speed that. Similarly with mu1 and mu2. mu1 and mu2 are a little nicer because they'll actually show you which port, the input port or the output port, you have stability issues with. So for instance, you can have a three-stage amplifier in the MMIC where you're getting K above 1, maybe much above 1, but you can still have linear instabilities even at small signal due to having a single stage, and it could be any of these stages that is not conditionally stable. So depending on where you actually match the input and the output, you could end up with an impedance at any of these stages that may be unstable. So when you're setting this up, if you do it such that you break it up between stage, you run a K factor on each individual stage, and then you look at, say, mu1, mu2, or K of each individual stage, that's actually sufficient to prove linear stability. Odd mode stability works fairly similarly. What we're looking for here in this case is loop gains that happen because of imbalances across the symmetry line, or even if you have a balance, you can get a loop gain depending on the actual matching conditions of the circuit. There's a number of ways to check for this. Two very common ones are based on work by Freytag and another one by Platzker. I'll refer you here to the actual analysis. But the point being, for instance, for Freytag, we want to be able to break along these lines of symmetry and look at the admittances at each of the input ports and the ports of the matching network. It's a fairly simple analysis to do once you've implemented it and have essentially a schematic set up for it. However, if you don't take the symmetry into account when you're first doing your design, you'll then have to go back, repeat this, redesign the whole thing in order to do it anyhow. So the earlier you can implement hierarchy in the design, the faster your design is going to go. Simulation for EM, obviously, it's the trade-off between EMing everything and the fact that we have limited timelines, and EM is not the fastest of things, although that is much improved over what it has been. But these things, what drives these? Frequency, compactness, complexity. Essentially, the higher in frequency go, the tighter we get, the more of an issue this becomes. So, yeah, lots of places you're going to need it. Just a quick demonstration, particularly as you move up into millimeter wave. This is just an output network on an output stage of a PA, and you can see there are a lot of places where this actually becomes an issue. At these corners, any place you have a bend, you can get an imbalance. You may need to shift this or straighten this out in order to account for phasing effects. Similarly, the phase from the feed port to the inner and outer FETs can be different, which can cause power loss and matching differences. Also, proximity effects on one side versus the other can both change your impedance and cause further proximity effects to cause phase shift across that FET manifold. So how do you account for that? Well, as opposed to using a single cell, which shows up in the schematic that has the manifold included and would not be able to be EM'd, you can break this into individual cells for EM, and then you could do your own manifold design, do an EM of that port, and you would be able to account for all of those issues and see how it's actually affecting your circuit. And this is a fairly simple thing to do if you account for the symmetry early on. Thermal, I would be very brief about this. It's obviously an iterative process. You need to make an estimated guess of what your base temperature and your thermal resistance are. The problem is that the thermal resistance isn't something that we can just tell you. It's going to depend very much on your actual layout and on the stack up below it, what you're mounting it to. So the iterative process, basically you estimate your dissipated power, build an FEM model, you're going to run a thermal simulation, and then you're going to feed back your calculated thermal resistance into your design and iterate until you close that loop. So for instance, in this case I used a base temperature 25, thermal resistance estimated at 25 ohms, put it into a simulator, found that my junction temperature for this case was actually about 139 degrees, which yielded a 28.5 degrees C per watt thermal resistance that got fed back in. and now I can use this in the actual simulation. This is very critical and very dependent on your actual application, particularly if you're using gallium nitride on silicon carbide, because of the nonlinear relationship of thermal resistance to temperature. So where your actual application is can have a big impact on what your thermal resistance is and what the junction temperature is actually going to be in the application. So design verification, just quick things. DRC violations can propagate. So if you get it early, you'll be able to account for it early, and they won't propagate. It'll save you time. Check early, check often. Off-grid errors are the #1 issue that we have with layout submissions, and it's a very complicated thing, but it's simple if you do the setup early. So I guess the main takeaway from all this is do all this stuff as early as you can in the design layout simulation. Design rules, obviously you need to check to make sure that you have them right. DC connectivity, this is a very nice tool. It's in AWR to make sure that you don't have gross DC errors. Again, check this often. LVS to compare your schematic versus the actual layout and make sure you don't have inadvertent shorts or connectivity gaps. Some stuff on avoiding off-grid issues. If you have time, I'd assume you'd like to read this. I would like for you to read this. Yeah. And in conclusion, #1, have a robust and flexible PDK. It's going to make your design process much simpler. Use hierarchy as much as you can to speed up both the layout and the simulation. Use EM, but be judicious in it because it is a time user. And start early with all of your verification checking. It'll speed up your process. So.